It's my great pleasure to introduce our second speaker of this nanomotor mini talk, and the second speaker is Lu Xianglong, who came from Professor Wei Wang's group in Harbin Institute and Technology, Shenzhen, and now he's joined Professor Martin City for PhD in Germany, and his talk will be on active yet little mobility. Asymmetric decomposition of hydrogen peroxide is not sufficient in preparing catalytic micromotors. So let's welcome Xianglong to share his research.
Okay, thanks for the very nice introduction, and good morning, good afternoon, good evening, everyone. I'm Xianglong Lyu from Harbin Institute of Technology, Shenzhen. Today, I want to share with you my recent work, active little mobility. Asymmetric decomposition of hydrogen peroxide is not sufficient in propelling catalytic micromotors. So as we know, catalytic micromotors or active colloids could move autonomously within a fluid by consuming external chemical energy. They not only demonstrate a great promise in applications such as drug delivery, environmental remediation, they can also be, but also they can be used as a popular system to study soft matter physics on a fundamental level. For example, collective behaviors. One archetypical macromotor is an inert microsphere half coated with platinum. By catalytic decomposition of hydrogen peroxide, they could move toward their inner side. Inspired by this macromotor, researchers have designed numerously catalytic micromotors by partially coated with various catalytic active species such as manganese, silver, enzyme, and platinum nanoparticles, which are catalytically decomposition hydrogen peroxide. So these macromotors seemingly leave us the impression that a macromotor can self-prepare as long as hydrogen peroxide is asymmetrically decomposition on the particle surface. However, here we show some compelling evidence that asymmetric decomposition of hydrogen peroxide is not sufficient conditions for propelling macromotors. We begin with a comparison in space between silica platinum film and silica platinum nanoparticles, which is prepared by annealing the silica platinum film in the argon's atmosphere, and after annealing, the gene structure and the potential of silica platinum microsphere remains largely the same. So we found that in hydrogen peroxide, the silica platinum nanoparticles move more slowly, and the trajectories show that melting the continuous film into discrete nanoparticles drastically reduces space by about 80%. Surprisingly, we found by measuring the oxygen generated from the decomposition of hydrogen peroxide, we found that the platinum nanoparticles showed better catalytic performance. And on the other hand, by systematically changing the thickness of platinum and annealing and annealed temperatures, a sharp decrease in motor speeds were also observed. We confirmed again that annealed samples often showed better catalytic performance. So the significant difference in the motor speed cannot be attributed to the difference in their catalytic performance, but to their surface morphology. And we found that silica platinum particles with coarsened platinum islands move faster than those containing discrete platinum nanoparticles. In addition to the platinum, the pole propulsion of genus microsphere described above is not limited in the materials platinum, but also applied to any system involving the catalytic decomposition of hydrogen peroxide. So next we prepared the silica catalyst genus microsphere, which could also rapidly convert hydrogen peroxide into water and oxygen. Similarly, by measuring the amount of oxygen bubbles, catalyst is comparable to the active platinum in its catalytic performance. However, its trajectories and mean square displacement data show that the silica catalyst genus microsphere just exhibits Brownian motion. Based on these above experiment phenomena, we believe that the asymmetric decomposition of hydrogen peroxide is not a sufficient condition to propel macromotors. Then we want to know how exactly the macromotors to move. To date, there are 4 driving mechanisms for catalytic macromotors, among which bubble propulsion is more likely for larger macromotors, commonly larger than 10 micrometers in diameter, so which outside the scope of this work. So here we mainly focus on the other 3 possible theoretic propulsion. The first is neutral self-diffuse surfaces, where macromotors are driven by a concentration gradient of neutral solutes, most likely oxygen. And the second is Ionic self-diffuse surfaces arising from charged intermediates such as protons or radicals, where motors are driven by the self-generated electric field that arise from the difference in the difference of diffusivity between cation and anion. And the third is self-electrophoresis arising from the electrochemical decomposition of hydrogen peroxide that happens on the surface of tapered platinum cap. Recently, people discovered the speed of platinum genus macromotors is sensitive to the ionic strength of solution. So people and our experiment results found that the speed of platinum genus macromotors decreases with the increase of concentration of salts. So that indicates that the neutral self-diffuse surfaces is a very weak effect. And as for the Ionic self-diffuse surfaces, we performed 2 simulations to showcase the effect of the surface morphology on motor speed. Theoretically, silica platinum film and silica platinum nanoparticles should have the similar speed if the Ionic self-diffuse surfaces is a dominating contributor, because after annealing, despite the continuous film is transformed into discrete platinum particles, they are still coated on the half of microsphere and catalyze similar amount of hydrogen peroxide, and they almost have the same Z potential. So silica platinum film and silica platinum nanoparticle would share the same chemical gradient and electric field profiles. And according to the simulation results, According to the simulation results, silica platinum film and silica platinum nanoparticle have the similar speeds when they are driven by the ionic self-diffuse surfaces. It is reasonable. However, this result is inconsistent with our experimental results. So ionic self-diffuse surfaces is also very weak. And finally, we suppose that self-electrophoresis may be the dominating mechanism. First, according to literature and our experimental results, we confirmed that the thickness of platinum spatulated on a microsphere is uneven, which is thicker on the pole and thinner on the equator. So the different thickness of the platinum, different thickness of the platinum layer leads to non-uniform decomposition rate of hydrogen peroxide, would generate a net current flow from the thick pole to the thin equator. To verify the assumption, we measured the current between platinum electrode with different thickness in hydrogen peroxide, and from the results, the positive value means that there is a current flow from the thick pole from the thick pole to the thin equator. Based on the results of electrochemical measurement, we performed a numerical simulation to showcase how the self-electrophoresis propel macromotors, in which the thick pole was said to be cathode, and the thinner equator was said to be anode, and oxidation and reduction of hydrogen peroxide will happen on the pole and equator respectively, generating a concentration gradient of proton. Then a self-generated electric field was set up to propel the macromotor to move toward its inner size with a speed of a few micrometers per second. After transforming the continuous film into discrete platinum nanoparticles, each of these platinum nanoparticles can be regarded as a nanocell, generating their own electric and flow fields, but these will cancel each other locally, leaving with global flows around the entire microsphere. So its speed decreases drastically, which is consistent with our experimental results. So we believe that self-electrophoresis is dominant for the motion of platinum James macromotors. To conclude, we propose that the non-electrochemical decomposition of hydrogen peroxide does not lead to effective self-propulsion at a micrometer scale, even if it occurs strongly and asymmetrically on the particle. This is supported by two evidence. First, silica platinum nanoparticle moved more slowly than silica platinum film, and the same experiment under the same experimental conditions, and the catalyst that does not power macromotors at a micrometer scale in the presence of hydrogen peroxide. So okay, so finally, I would like to thank my supervisor, Professor Wei Wang, for his guidance, and thank Professor Xinma and my group member for their help. That's all. Thank you for your listening.
Okay, thank you, Xianglong, for your last talk. Now let's see if we have question or comment from the audience.
Hi, this is Ayushman. I have a question.
Yeah.
Why do you know why the anode and the cathode depends on the thickness of the platinum layer? Why is one of them the anode and the other the cathode, depending on how thick the platinum layer is?
So sorry, I can't follow you. Can you repeat your question?
Well, you're saying that for example, where the platinum layer is thick, that's the cathode, and where the platinum layer is thin, it's the anode, right? And the question is, why does the thickness of the platinum layer decide what is the anode and what is the cathode?
What is the anode and what is the cathode?
I'm asking why the thickness of the platinum layer decides what is anode and what is cathode.
Oh, okay. The thickness is we prepared the genus microsphere by sputtering vertically. So on the pole, the thickness of the platinum, the thickness of the platinum is thicker, and on the equator, the thickness of the platinum is thinner. And according to the literature, the thicker the platinum film and their catalytic, the higher their catalytic performance. So according to our results of electrochemical measurements, we confirmed that the thick platinum film served as a cathode, and the thinner platinum served as a anode.
Okay, thank you for your answer.
Yeah.
So any more question from the audience?